Hello everyone, my name is Xing and I am a PhD candidate in the Computer Science Department at University of Minnesota. Today I will be talking about Firefly, Untethered multi-user VR system for commodity mobile devices. This is a joint work with my colleagues at University of Minnesota and Hewlett Packard Research Labs. Virtual reality is becoming increasingly popular and has registered numerous applications. When a common user wants to experience generic VR, he or she typically has following options. The first one is traditional cable VR, for example, Oculus Rift. It requires a dedicated PC to perform rendering. If we project this option onto an evaluation system, we can see that it has high rating on performance. The user mobility, on the other hand, is bad because users are wired to the PC. It also costs a lot of money and deployment efforts because we need not only the headset, but also a rendering station. Because of these drawbacks, this approach is hard to scale and support multi-user VR scenario, for example, co-location group gaming. The newer generation of all-in-one VR solution like the Oculus Quest partially address the issue. However, it is still relatively expensive, especially consider multi-user VR scenario. One alternative approach is to leverage the smartphone in our pocket. It could be plugged into a dummy head-mount display like Gear VR and Google Cardboard. In this case, all computation happens locally on smartphone. This approach enables good user mobility by cutting the cord. The cost is also low because we can buy a Google Cardboard as low as $10. It also has the potential for easy deployment and multi-user scalability. However, this approach suffers severely on the performance dimension because mobile GPU is usually weak. So the real question is, how can we support multi-user VR on smartphone by introducing minimum system components and deployment efforts? In fact, there are recent works trying to improve the performance of VR on smartphones. For example, the first one, Flashback, is a local VR system for smartphone that employs aggressive pre-rendering and local memorizations to overcome the real-time overheads. And Foreground is another system whose main idea is pipelining and offloading the rendering task onto an edge server. So those work partially address the performance issue. However, they were focusing on a single user VR scenario, leaving the multiple user scalability challenges unexplored. We therefore design and implement a system called Firefly. Firefly is a low-cost and easy to deploy co-location multi-user VR system that supports more than 10 users to simultaneously enjoy high-quality VR content with the support of single server and Wi-Fi access point, a bunch of commodity smartphones, and cheap VR headsets, for example, Google Cardboard. So our target is 60 FPS with low motion-to-photon latency and decent image quality. So Firefly enables use cases, for example, team training, group therapy, collaborative product design, and multi-user gaming. Of course, our ambitious goal poses numerous challenges to the system. For example, the mobile GPU is far from powerful enough to support heavy-duty rendering tasks for high-quality VR, and the smartphone has stricter constraints regarding energy and heat consumption. The heterogeneity in computing capabilities of these devices is another factor we need to consider. And finally, we need to answer questions regarding multi-user scalability challenges. For example, how do we split the client-server rendering workload, and how do we overcome the single access point bandwidth limitation? Here is an outline for the remaining part of this presentation, and I will start by giving an overview of the base solution we adopt in Firefly system. We consider three high-level system architectures. The first is a serverless design, and in this case, the full-fledged rendering happens at the smartphone. So previous study has indicated that today's smartphones are far from being powerful enough to do this. The second option is edge offloading. In this case, the server performs real-time rendering for the client and encodes the rendered content into VR frames and streams the encoded VR frames. This approach involves overwhelming rendering and encoding overhead for the server side. So in particular, we studied the encoding overhead for single server, and we find that even with a pretty powerful workstation, the encoding output is only 150 FPS for high quality image. Consider each user requires 60 FPS, this approach apparently does not scale. So the third option is to perform one-time exhaustive offline rendering, and during the offline stage, we could prepare all possible VR viewports that the user could see and encode them as video stream. And during the online process, we can stream the encoded video frames based on users' VR motion. So this approach entirely limits the real-time rendering and encoding overheads and could scale to tens of users at the cost of high memory, disk, and potentially networking usage. So we adopt the third options as our base solution and apply multiple system optimizations on top of it. Next, let's look at individual components of the Firefly system. We realized the previously mentioned offline rendering by offline rendering engine. So the high-level idea is that it discretizes the whole VR space into smaller grids, and at each grid point, we render a panoramic VR frame, which includes the whole 360-degree view information. At the client side, the panoramic frame could be projected onto a sphere to create an immersive VR experience. In our actual implementation, we render both the color and depth panoramic frame, where the color is for display and the depth information is for overlaying dynamic objects onto the background layer. The color and depth frame are stitched together into what we call a mega frame. The mega frame is being splitted into multiple tiles, and each independent tile is being transmitted and decoded by itself. So by streaming at tile level, we have finer fetching granularity, and we can strategically save bandwidth because we can always discard the tiles that user cannot see. So we apply the offline rendering engine onto two typical VR environments, which are office and museum. Their map size is roughly 30 by 30 meters, and we adopt a rendering grid size of 5 centimeters, and the final render size is 137 gigabytes for the office and 99 gigabytes for the museum. Now we have the whole VR space rendered as tiles and encoded as video streams. The next question is how the client should fetch tiles. So before answer this question, let's first understand the VR motion. With generic VR, users are enabled with 6 degrees of freedom, which means users can perform both translational movements on XYZ dimension and rotational movements on the yaw, pitch, and roll dimension. Based on this, we pretty much built an offline mapping. Basically, each tile could be indexed by the combination of VR sensor data, and very intuitively, we could fetch tiles based on users' VR motion. Now let's do a quick end-to-end latency breakdown. So on average, from requesting the tile and until the tile is seen by user, it takes 17 milliseconds, which consists of the requesting, transmitting, decoding, and rendering delay. On the other hand, if we want to achieve 60 FPS, the interframe delay budget is only around 17 milliseconds. Clearly, we need motion prediction in order to prefetch and compensate this end-to-end latency. To better understand the predictability of VR motion, we did a VR user study. We invited 25 participants to our study, and during each trial session, user can freely explore a customized VR application which is developed with Unity API. The apps renders previously mentioned environments, the office and the museum, and each user is equipped with a full-fledged Oculus Rift, which enables the 6DOF motion while users were exploring the VR space. So we record the user's 60 DOF trajectory, and in total, we collected 50 traces, with each one has a duration of 5 minutes. The left-hand side shows the bird's eye view of the user's translational trajectory among the two different VR environments. As you can see that users were highly engaged and indeed explored the whole map. Their translational trajectory were quite diverse, suggesting the different interests among users. The right side plots the rotational velocity for randomly picked 5 users, which also shows decent level of diversity. We apply a simple linear regression model with a historical window of 50 milliseconds and a prediction window of 150 milliseconds to validate the predictability of VR motion. The plots here shows the CDF for prediction mean absolute error for translation and rotational movements. So for the rotational movements, we generalize the yaw, pitch, and roll into latitude and longitude for simplicity. The median value for translational MAE is 1.4 centimeter. This is actually pretty accurate given the translation granularity is 5 centimeter. The median value for latitude MAE is 1.9 degree, and for longitude is 7.6 degree. This is also acceptable given a typical field of view is 100 by 90 degree. We then apply this linear regression model to our online prediction module. The idea is we predict each dimension separately. We combine the results to present a final predicted viewport, and then fetch the minimum amount of tiles trying to cover this predicted viewport. We also characterize the VR user's stationary periods. So during a stationary period, user performs no noticeable motion either translationally or rotationally. Within a 5-minute VR session, we find that an average user spends around 43 seconds being stationary. Those stationary periods are short but also frequent. The median duration is around 1 second. So one setting fact of those SP is that the transition from stationary to moving results in sudden movements, and it makes the prediction unavailable. To address this, we basically implemented 2 prefetch modes. So when users are moving, Firefly prefetch based on the most up-to-date prediction results. And when user is not moving, Firefly will prefetch all surrounding or neighboring tiles in a best effort fashion. So Firefly also incorporates other optimizations to observe the inaccurate prediction. For example, Firefly heuristically enlarged the predicted viewport. And for more detail on this, please refer to our paper. So the takeaway message of our user study is that the user's VR motion profiles are diverse, and the continuous VR motion shows good predictability. However, we need special mechanism to handle the sudden movements and to observe the inaccurate prediction. Now let's walk through the Firefly system architecture. In the offline phase, the rendering engine pre-renders the VR space and populates the content database with encoded tiles. During runtime, Firefly runs a lightweight motion predictor at per frame level. The tile prefetching scheduler interprets the predicted motion trajectory into a ranked list of tiles and requests them from server side. When deciding the priority of each tile, we consider both the visible area it covers and also the display deadline it inherits. At server side, the AQC module is the key component to help Firefly scale more users. The rationale is that for each tile, we prepare multiple quality versions offline. During runtime, AQC takes as input the available bandwidth and the user request, and then decide the appropriate quality level streamed to that user. The desirable features of AQC is that for each user, it should maximize the quality level while minimizing the stall and the quality switch. It should be fair to different users, which means the streaming quality should be proportional to the available bandwidth to that user. It needs to be executed in a fast-paced manner, and it should scale more users. Ideally, AQC can follow an optimization scheme where we try to maximize the global utility function. However, because AQC is executed at peripheral level, we therefore take a more lightweight heuristic approach. Now let's walk through the logic of the AQC algorithm. The AQC is triggered every 15 milliseconds to adapt to the fast-paced motion updates. During each invocation, AQC first obtains the available bandwidth from access point. Those represents both the global bandwidth capacity as well as the local throughput constraints for each client. Then, starting from the most recent assignment, AQC tries to either increase or decrease the quality for selected user until both global and local bandwidths are fully but not overutilized. There are two design decisions worth mentioning here. First, when selecting which user to adjust quality, we use least risk used strategy to facilitate the fairness among users. Second, we reserve a default bandwidth for users that are currently stationary in case the system don't have enough capacity once the user starts moving. After the client receives tiles, they will be cached in a hierarchical manner based on the display deadline. The L1 layer, which lives in video memory, caches the decoded tiles which can be directly used for display. The L1 layer is the fastest but the smallest. The L2 layer is in main memory. It stores the to-be decoded tiles. Additionally, all tiles will be swapped to L3 disk after expiration. In this way, if the user revisits the tile that the client already received, there is no need to request again. The tile decoder consists of concurrent hardware-accelerated decoders. It is responsible for tile decoding. Finally, the renderer is responsible for projecting the tiles onto a sphere and further overlaying dynamic objects. Now let's talk about how Firefly handles dynamic objects. The example of those foreground objects are other users' avatars or a control panel that user can interact with. Firefly rendered the foreground objects locally on client in real time, and this is because of following reasons. First, the interactive nature makes pre-rendering for objects not feasible. Second, the foreground objects requires less rendering efforts compared to the complicated backgrounds. And third, the dynamic content is more sensitive to latency. Therefore, we decided not to perform server rendering to eliminate the networking uncertainty. It is still possible that object rendering could become the bottleneck of the system if there are simply too many objects. In this case, we apply an adaptive object rendering scheme. And the high-level idea is that before runtime, we prepare simplified versions of each object by reducing the polygons. And during runtime, we can make dynamic decisions about the object rendering quality based on demand. For more details about this part, please refer to our paper. Next, we discuss the implementation and evaluation of the Firefly system. We have implemented the full-fledged Firefly system. The offline rendering engine is developed with Unity API and FFmpeg. The client is implemented with Android SDK. We use Android Media Codec for tile decoding, OpenGL-ES for projection and rendering, and OpenGL frame buffer objects for L1 cache. The server and AQC is written in Python. We use a replayable experiment environment by using 15 devices to represent 15 concurrent users. We run the Firefly client on 5 real smartphones and 10 Raspberry Pi. The server and the access point co-locates in a VR lab, and all the clients were randomly distributed in the lab. The high-level approach is that we simultaneously replay the trace we collected in the user study on 15 devices and log key metrics to evaluate the performance. Let's first discuss the overall performance of the Firefly system. Here we compare Firefly with two different variants. Foreground is the state-of-the-art single-user VR system for mobile device. We leveraged Firefly infrastructure and developed a multi-user version of Foreground. The perfect variant demonstrates an ideal case when the viewport prediction is always accurate. We basically utilize the Firefly system with perfect prediction to locate the upper bound of the system performance. The metrics we evaluate include FPS, stall, content quality, motion-to-photon latency, quality switch, and fairness among users. Here I will only highlight some key results. First, Firefly achieves overall good performance across all the metrics. It significantly outperformed Foreground and only slightly underperformed the perfect prediction. In terms of FPS, 90% of the time the FPS is greater than 60, and 99% of the time is greater than 50. The user perceived stall is only 1.2 seconds per minute, and the bandwidth consumed by 15 concurrent users is less than 200 Mbps. This means there's still room to scale more users with even single access point. The achieved average content quality is Quad HD with an average CRF of 23.8. So CRF stands for constant rate factor. You can think it as the encoded bit rate of the content, and the lower CRF represents a higher quality level. We also leveraged comprehensive micro benchmarks to showcase the impact of key design decisions of the Firefly system. For example, we investigate the impact of AQC, the impact of bandwidth reservation for stationary periods, the impact for different viewport prediction strategy, and the impact of adaptive object quality selection. So due to time limits, I will leave those in our paper. Next, we use two case studies to demonstrate Firefly's resilience to fluctuating networking and number of user condition. So the first one is the adaptiveness to number of users. So during a 5-minute VR session, we start with 5 concurrent users. We then gradually increase number of users to 15, and then gradually decrease back to 5 at the end. So the left side shows the average FPS across all users over time. We can see that Firefly still maintains above 60 FPS while users were either joining or leaving the system. The right side shows the average content quality across all users. And we can see that when number of users is less than 10, Firefly can achieve the highest quality of CRF 19. And when adding more users, Firefly adaptively lowered the quality and to make sure tiles can still be delivered efficiently to maintain a decent FPS. In the second case, we study the adaptiveness to network fluctuation. So during a 5-minute VR session, we throttled the global bandwidth to 140 and 100 Mbps respectively. We observed the average FPS and content quality of 15 concurrent users. We can see that in both cases, Firefly adaptively adjusts the content quality to lowest level, and when the network is throttled to 140 Mbps, Firefly can still achieve FPS above 60, and when it is further throttled to 100 Mbps, even the lowest quality cannot sustain 60 FPS. We use different smartphones to study the energy and thermal overhead of the Firefly client. With a fully charged smartphone, after 25 minutes of Firefly client usage, the battery left is between 92 to 96%, and the GPU temperature is less than 50 degrees Celsius. To summarize, we have demonstrated with Firefly for the first time the feasibility of supporting 15 VR users at 60 FPS using commodity smartphones and a single server and access point. Our design makes judicious decisions on partitioning the workload, making the system adaptive to available resources, and handling VR users' fast-paced motion. We believe the core concepts of Firefly system can be also applied to other multi-user scenarios for augmented reality and mixed reality. That concludes my presentation, and thank you for listening.